Welcome to step three of the series that we're talking about in terms of AI strategy and how to make an effective AI strategy and how to be successful at it from day one. Step three is data, which is actually the key ingredient of anything you want to do with AI, machine learning, any statistical sciences, because if your data is all messed up, your models are messed up. If your data is good, your models are good. But then again, how do you identify which data to use, whether the data is good or not, what makes sense, what to drop, how do you optimize, a bunch of different things you could do with AI itself. So let's move on. So, having said that, let's firstly quickly recap why do AI projects fail when they don't have too much data maturity. The model fails because you are training on low quality data. You're training on data that perhaps just doesn't even make sense or has a lot of redundant information. So that's one reason. The next one is you have challenges with scaling because a lot of times when you train on data, you probably have the data available to you as in your storage, but in real time, you may not get that data in the same form that you were expecting it to be on which you trained your model. So, for example, if you figure out a particular medicine helps save the life of a patient, you may not know that before the patient comes in for a diagnosis because now you don't know. And if you've trained your model based on that medicine, then there's a fair chance that you will miss that entirely in production because that data is a post facto rather than being available to you prior to the patient coming in. The next one is poor outcomes. Now, what ends up happening is many a times you have a data that is so nice, pristine, that you end up overfitting the model to your particular use case and the data that when you take that into production, or even when your experiment might be successful, but when you take that over to production at a larger scale, you will start seeing a model misbehaves completely and you may just have to turn it off. So there is definitely a need to understand your data and ensure that the data that you have in your environment right now for training is what you would also have in production. And again, a lot of this results in trust deficits because that's where your stakeholders lose confidence. Imagine getting a data, starting to train, putting it into production, figuring out it's not working, doing this thing back again, and going in loops without making too much progress will erode the trust from your stakeholders. So that's one thing to really be careful of. And this is stakeholder disappointment is by far a very big factor, contributing factor to AI projects failing. Data over a period of time, you will understand, you will do some experiments, etc. But once the the stakeholder confidence is lost, it becomes very difficult to get it back on track. Anyways, so moving ahead. Um, okay, yes. So what are some data sources? And again, this is just example of like 80-20, 80% of the data is this. There are 20% of the data is other things as well. So you have a long tail. Generally transactional data, which you get as part of your transactions, orders, payments, purchases, bill payments, etc. You have data in your archive logs. For example, if you're predicting things around predicting an error in your production system, you may want to look at your logs. You may want to look at data that is streaming. So, for example, if you have an e-commerce website and people are coming onto that website, you may want to look at streaming data. Where are they clicking? What's the session time? Which pages? How much time between different clicks? What are they really doing on the website? If it's a mobile app, what like do they tap on the notification to get into your app, or do they log in on a daily basis? What are they currently doing? Is there an activity of interest that they're currently doing on the app? A bunch of different things. And then you have engineered features because this is where you understand the data, you understand the crux of the business, and from there you derive features that are key to your like intuition. Based on your intuition, you go ahead and derive those features. And only when you understand the data well and the business context very well, you will be able to build your intuition and arrive at new features or new data types combining, or new data models combining data from different aspects of it, right? So for example, you may want to combine city or churn you generally predict, but maybe say city number of customers in that, and maybe like an average session time, for example, if that is important. You may want to combine all of this into one field or one feature, which could be weighted based on some of these combinations, so that now becomes an important moot point for you to build your model on. And again, this is a very hypothetical example. In reality, you really have to understand the data to build that intuition. And then you could also look at third-party data, which is weather. For example, if you're building a model about predicting, um, let's say, orders for a particular type of product, right? You may want to factor in weather. So, for example, if you want to predict the sales of an umbrella, you really have to look at weather. Or if there are certain things that are seasonal, you have to look at that season. If you don't factor that in, generally what happens is your model is completely biased. It'll give you facts and numbers, resulting, like, getting you into a process of either over investing or under investing, and both of them are very bad for business, right? Also, another one is human generated. When you look at reaching out to people, asking for NPS scores, or a bunch of different other factors where you're surveying them, you're going and looking at what they've spoken with your customer care. You could look at some signals, key signals from there, and figure out the general trend of the consumer and whether they are happy with you, with your product or not. So that social listening is extremely important from that perspective. Okay, moving on. Now, what do you really generally do to choose the right training data, right? The first one is you have to understand what you want to keep. If you have data that is recent and it's relevant, keep that. And if that recency and relevancy of the data is seasonal, keep that. If you're looking at a trend which is 5 years old and you're trying to predict a model based on 5-year-old data, there's a fair chance that trend has changed over a period of time. And if you don't understand that well about your business, then there's a fair chance you're just approaching it purely from a science mindset, a statistical mindset, as opposed to understanding the business context. So you need to know which data to prune as well. The next is structured information. Rarely do you find structured information nowadays. A lot of models are getting built with unstructured data, but yes, you need to keep structured data. If the data is unstructured, figure out a way to get it into a structure, because your data frames and your models generally will depend on that. The more structured your data is, the better your outcome is. Otherwise, it just becomes slightly challenging to validate the data, and then becomes a black box model. Then you have to build certain techniques, etc., to roll back and figure out, or not roll back, to work backwards and figure out what could have gone wrong, or what is the contributing factor to that particular output. And also, you need to have features aligned with the prediction. Like I said, do feature engineering. Many times you will need to do feature engineering, without which it's impossible for you to build a good model. So you could build a base model, which features that you get. And then once you understand how these different features impact the overall scores of prediction, you can then, based on intuition, come up with your own features, a combination, an aggregated feature or a weighted feature, to then, once you do that feature engineering work, you then use that to build a model and then have a better output. What you generally remove is redundant IDs or data that just doesn't contribute to your output. So there is a fair chance, like, for example, I'm going to be talking about it in the next slides. But for example, if your data has column city and 95% of the records belong to a particular city, it's just redundant. Just get rid of it, right? You really don't need it. The cardinality is a challenge out there. So you basically get rid of it, because it's just going to bias the model completely, right? If you have redundant data, for example, you have feature A and feature B, which are redundant to each other. Generally, you should drop one of them, because one contributes to the other and vice versa. So reduce the size of your data frame to have faster iteration cycles on your model building as well. You also remove unlabeled junk. Like, if you have data that it's not labeled at all, or you don't know what to do with it, just remove it. Pointless breaking your head on it. The next aspect is about target leakage. Now, generally what happens is you are looking at building a model, like I said earlier, based on facts that you are already aware of in production environment. But generally, when you deploy the model, you don't know that fact yet. And if you try to have a target prediction score based on data that you don't have in production, but then you've used that to train your model, that itself is a conundrum, because you're looking at having the data to make a good prediction, but now you're expected to have a prediction without that data coming in. So that is a post facto, pre facto that I was talking about. And I'm going to be talking a lot more about some of this and techniques, etc., from a future standpoint as well. I mean, in more videos, of course. So the key principle is train the model based on the data that you get in production. If in production you don't have the data, please do not even bother training that model on that feature. Moving on, how do you then generally measure the feature and the importance, right? There are several methods. I've just picked up the ones that I generally use or I have used in the past. SHAP, Permutation, Gini, and Lime. So SHAP basically is a method to help you figure out the score or assign a score to your features, which says if a particular feature A, what's the score of this feature that results in the prediction that has been made. So if it's like say 0.35, 0.4, then perhaps keep that. If it's lower, perhaps you may want to eliminate that. Right. So every feature is scored so that you know what is the importance of every feature in the target score that you are looking at, or the prediction value that you're looking at. The next one is permutation. So for example, if you think that a particular feature should ideally, based on your intuition, play an active role in the prediction, uh, let's see if we just go ahead and reshuffle or just completely shuffle the entire column. With that, what happens is if the shuffling reduces the score, then there is a fair chance that feature has a role to play. If shuffling doesn't do anything to the output or just changes it just very minutely in a very narrow band, then there's a fair chance that feature is not important at all, and it's okay. You just drop it. It's not going to make a difference to your final model and the prediction in any ways. The next one is around Gini or MDI, right? Mean decrease of impurity. Now, this is mainly used for decision trees. Now, what happens is a decision tree is made on based on a data, and there are branches that come out of your data based on different conditions of those features. So, for example, if salary is an important one, less than 10,000, greater than 10,000, then within that greater than 10,000, between 50,000 and less than, like 50,000 as a moot point, greater than 50, less than 50, but also greater than 10,000. So this is how you generally build your decision tree. Now, what happens is it helps you understand from a categorical standpoint, may not be too much on the numerical like I explained, but on a categorical standpoint, what is a good decision boundary? Where does your data split well? And what is the moot point where the prediction output continues to improve at what point? So that basically helps you understand at a level of decreasing impurity, where do you really draw a line? Because you could just have a very like a narrow, how do I explain it? So you could have a very detailed decision tree, but that's where you try to then overfit the data. You want it to be slightly abstracted, generic. So this particular technique helps you understand where to draw the line and where to stop. The other one is Lime. When you have a prediction, you just don't know what happened. So what you do is you build a local model to reverse engineer what could have happened to get that output. So it basically helps you with understanding explainability of the prediction, etc. So these are certain features. I'm going to be going very deep into all of this in the future videos. So again, a quick reminder, if you've not subscribed, please do subscribe so that I can continue to keep posting more videos like this, and you can learn with specific and practical examples of all of these and more that exist from a importance, feature engineering, and AI/ML standpoint. Okay, moving on. Uh, Also, when you have features, you would want to remove the low value variables, because if a particular feature does not result in a very high confidence of your output and it has a very low value, it's better to just get rid of it, because that is not going to do too much to your final output. Now, there are several techniques. I'm just going to list down a few that are important and I've used in the past, and I myself am learning more, so I'll keep sharing more and more as I keep learning. Variance thresholding, right? What you generally do is, like I said in the past, if your variance is not too high, like your cardinality is just like, for example, if a particular field has 90, 95% of the same cities, there is very little variance, just get rid of it. The next is correlational analysis. If two columns have very high correlation with each other, so you could decide to keep either of them because they mean one and the same, right? The next is around recursive feature elimination, wherein if you look at SHAP, the SHAP values that I spoke about in the past, in the previous slide, if you look at that and you recursively eliminate features from the model and figure out what your confidence score is, what your final predictive value is, and like the accuracy scores basically. And if the accuracy scores further improve based on elimination, now you know which columns really help or which features help versus which features don't help you or does not do too much in terms of contribution. So you could basically decide to get rid of it because that helps you overall optimize your model and also make your training process faster. The next one is mutual info and ANOVA. We'll talk more about mutual information. ANOVA needs a very dedicated, section in itself, so I will cover that in the future. Now, mutual information is if one variable means the other, right? For example, you could look at a call center log. If you're predicting churn and you're looking at how many times the customer called before the churn happened, let's say that's how you want to approach this. So if the customer called 10 times and the churn happened versus 0 times and the churn didn't happen, perhaps there is a good mutual information there, right? So you could potentially use that field. But if the customer called 10 times versus called 0 times, but the churn is still very high, perhaps that column or that field or that feature is really not helping you at all. It's better to just drop it. It doesn't have too much value. Now, ANOVA again is purely based on categorical information. So when you have a categorical information, your ANOVA scores help you really understand where the split happens, how is it that particular split is adding value to it or not. Again, it's a detailed topic in itself. I'd love to do this with a proper example, love to do it with a proper notebook. So more about it in the future videos. So what are some final key takeaways? Good AI is that equation is good data times smart feature design. So it's just not about your data. Of course, data is important, but also how do you leverage your data? How do you leverage these different fields and the values of your data? Are you able to do feature engineering? Are you able to prune the data to a level where you really can get a data set on which you can train a better model? That's important. What you should then also do is you should measure and you should continue to keep a track history, like a lineage, first data lineage and also a model evolution lineage to understand what have you done with the data to get to a particular score so that when you look at it at a holistic level, you can identify what contributed to which score and then pick and choose only those that really make sense to your model. But also when you're doing that, keep in mind that data that you choose should ideally and always be in your production environment, without which your model is going to fail from the get-go. It's pointless to then put this model into production. And also, when you're building this, you don't know what you don't know in production environments while you've done all your precautions, you've done everything wonderfully well for yourself. But if you're taking this to production, always take it as a small pilot, make it non-committal so that it perhaps works in the shadow so that you can understand what's going on. And if something does go wrong, that's okay. It is just an experiment. You can roll it back, come back, reevaluate, and then apply it again. So that's all that I have to say in this video, data being the key. Thank you very much. If you've liked this video, please like and subscribe and also share it with your friends. I'm going to be covering more on AI strategy. And also now going ahead, I will start to talk more about different concepts, go deeper into different topics, sciences, methods, with notebooks, with examples. So thank you very much. Thank you for watching.